What's up, mathematicians? Justin here, and in this video we'll be looking at some more advanced applications of trigonometry. Now, before we get started, I should probably point out that the term advanced is relative. These applications will be more advanced than the applications we looked at in the last video. However, applications of trigonometry can get far more advanced than what we'll be looking at in this video. With that said, let's look at our first example. This is the first more advanced application, and this one is actually not too much more advanced than what we've already done. I'm going to go ahead and draw out a little diagram here. So in this diagram we have a person and the ground, and we're going to say like that there's some building, and on top of this building is some antenna tower, something like that. Okay, and so the person is 90 meters away from the building below where the antenna tower is. I guess we should include that. Now the person does have some height, but turns out we won't actually need to take that into account in this problem, and we'll see why later. Now the person will be looking straight ahead along a horizontal line. This is the horizontal line that the person's looking from, and we'll take into account two different angles of elevation. The first angle goes to the top of the building. The second angle of elevation we'll be looking at goes to the top of the antenna. Now we'll just say that this person's goal is to determine the height of the antenna. So not the height of the building, but the height of the antenna. So that length right there, we'll call that x. And now we need to specify some angles. So the person has some device for measuring angles of elevation, a transit, a phone, that they line up or something like that. And we'll say that this angle here, they measured, an angle of elevation they measured to the top of the building is 17 degrees. So we'll say that's 17 degrees. But then we have this bigger angle of elevation, which includes this one, but also includes the extra to the top of the antenna, and we'll call that 22 degrees. We'll say that was a 22-degree angle. Okay, and as I said already, the goal is to find this height right here. Now, you can see that we have a right triangle. If I put that in there, we have a right triangle here, but this side right here is not part of the right triangle. So we're going to need to get a little bit more creative. What we can do relatively easily is find this length right here using techniques that we are familiar with. So let's just call this h for height, even though it's technically not the height of the building or the height of the antenna, really anything, because it doesn't include this extra bit here, the height of the person. So if we look at h as this height, we will see that we have, if we look at the situation, we have enough information to do right triangle trigonometry because we have one side length and one angle. We have the two pieces of information needed, right? Remember, we need at least two pieces, at least one has to be a side length. So we can go ahead and write out our three, and I'll write them over here. So what's the opposite? What's the adjacent? What's the hypotenuse? Well, let's see. The opposite length is h. And I realize that's getting a little confusing because I have h here and h there. Maybe I should just call this y. Just use a different variable. Let's call that y. Call this y. Okay. So now the adjacent side is 90 meters. It's not the hypotenuse, but it's touching the angle. So 90 meters. Okay, and then what is the angle? Well, since we're going for this full distance y, it's the bigger angle, 22 degrees. So since we don't care about the hypotenuse here, we're going to say that using opposite and adjacent, I don't know if I have this readily accessible here, but just to remind you, opposite over adjacent means we're going to be using the tangent function. So the tangent function, all right, the tangent of the bigger angle, 22 degrees, is equal to the opposite over the adjacent. So y over 90. Now we just do a little bit of algebra, multiplying both sides by 90. And I can plug this in my calculator, and I will get, let's see, 90 times the tangent of 22 degrees. That's 36.3, we'll say 36.4 meters. So 36.4 meters. Okay. So again, that's this height of most of the building and all of the antenna, but not this little bit right here. Well, that does not tell us the height of the antenna. We also are going to need to know this height right here, right? And so maybe we call that Z. And if we look at the opposite, the adjacent, and the hypotenuse for Z, once again, we know the hypotenuse is not something we care about. The opposite to the angle, this time it's a 17-degree angle, is going to be the length Z. The opposite, or sorry, the adjacent is still going to be 90 degrees, or sorry, 90 meters. And I don't care about the hypotenuse. So once again, I'll use the tangent ratio. So now I'm going to say, okay, 90 times the tangent of 17 degrees, because I'm getting this height right here, is equal to, whoops, sorry, I skipped ahead there. The tangent of 17 degrees is equal to the opposite, which is Z, divided by the adjacent, which is 90. So do the algebra, multiply both sides by 90. And now I'm going to see that Z is equal to, let's go ahead and plug it in, 90 times the tangent of 17 degrees. Okay, so here we have 27.5 meters. Okay, so 27.5 meters. Okay, if we look at the picture here, we can see that this length X is the length Y minus the length Z. Now, by the way, Z is, again, not the height of the building. If we added in the height of the person, you know, whatever they are, if they were 1.5 meters, for example, then we just add 1.5 meters to get 29 meters for the building. But we don't actually need to worry about that. All we need to do here is take this length here, Y, and subtract Z. So X is equal to, based on the diagram, Y minus Z. And we can go ahead and plug that in. 34.6 minus, I don't know if you can see this, 27.5. And that gives us 7.1. So 7.1 meters. So the height of this antenna, given these, these distances and angles specified, would be 7.1 meters. Okay, now let's take things up a notch, or maybe a couple notches. We're going to look at an example of how we could use the trig ratios to find the height of a hill that we can't measure, like we can't get to the base of, basically. But it's a hill that has a flat, sort of a flat piece of land, a flat field below it. So let's draw our diagram first. So basically we've got some ground, and we'll say that this ground is on some field or something, and that's flat. And then eventually we see this sort of hill come up above the flat field. Now, we'll pick two spots on the field, here and here. And we'll say that the distance between these two perspective points is 120 meters. Okay, now I'm going to draw lines, drawing some triangles here. Okay, so we've got a line from the further point, perspective point, and then a second line to the closer perspective point. And let's go ahead and draw in our vertical line as well. Okay, so thinking about this situation, if we think about it, it's not too hard to see why this is a challenging problem, because I want to know this height, the height that the top of the hill is above the level of the field. But in terms of taking measurements, I can certainly use a transit level or something similar to find these angle measurements. But I can't find the distance from here to here because this is under the ground. I can't, like, you know, I can't dig. I'm not going to tunnel all the way through to the, I mean, I guess maybe I could, but then how would you know you're under the highest spot even? So that would be a much more difficult proposal, you know, to try to get underneath the ground, deep under the ground, below the highest point of that hill. Okay, also the distance, if I could find the distance from here to here, that could help, but how would I do that? I mean, would I take a really long cable and stretch it? You know, this is not an easy proposal. If it were a small distance, maybe you could take a piece of rope and just stretch it across and then measure the rope. But that's challenging too. So, you know, I don't know this, I don't know this, and I don't know this. And remember, we need to have at least one side. Otherwise, we're stuck. There's nothing more we can do. So let's think about how we can use a little bit more algebra to make these different lengths, distances accessible. Let's call this length x, and now we have another length right here, right? And we'll call that length y. I also need to specify these two angles, so we'll say that this first angle is 7 degrees, the second angle is 13 degrees. So, you know, some observer went to these 2 points 120 meters apart and used some device to measure the angles of elevation at those 2 points, got 7 degrees and 13 degrees. And now if I look at this situation, I can sort of see something I can do, because this whole distance here is 120 plus y. And so if we think about the 7-degree angle, so let me see, I'll write it here. So from the perspective of the 7-degree angle, the opposite length is x, and the adjacent length is 120 plus y. So 120 plus y. Okay, all right, and the hypotenuse I don't care about, so I know I'm going to be using the tangent here. Now let's look at this smaller triangle. So we got the big right triangle with a 7-degree angle, now the smaller right triangle with a 13-degree angle. For the smaller right triangle, the length opposite the 13-degree angle is once again x, and the adjacent length is y. Okay, so what that means is that the tangent of 7 degrees is equal to x over 120 plus y. And the tangent of 13 degrees is equal to x over y. So if I can get these two x's by themselves, I can set the two equations equal to each other. So let's multiply both sides by y here. And here I'm going to multiply both sides by 120 plus y. So those cancel out and I get 120 plus y. So now this is equal to x and this is equal to x. These are two separate equations, by the way. So I get that 120 plus y times the tangent of 7 degrees is equal to x, which is equal to y times the tangent of 13 degrees. Okay, now we're getting somewhere. If I can get y by itself, I can actually find this length, and then I'll have this side, and then I can find the height. Okay, so now let's go ahead and distribute this. So I'm going to have 120 tangent 7 degrees plus y times the tangent of 7 degrees is equal to y times the tangent of 13 degrees on that side. And all right, so 13 degrees. So then we have these two y's here. Let's subtract this one from both sides. So subtract y times tangent 7 degrees and subtract y tangent 7 degrees. Now I'll be able to factor the y's out on this side. And I'll have 120 tangent of 7 degrees is equal to, factor out the y's, and I have y times the tangent of 13 degrees minus the tangent of 7 degrees. All I have to do now is divide both sides by this, tangent of 13 minus tangent 7. So tangent of 13 degrees minus the tangent of 7 degrees. This cancels out with this, and I have the same thing on the other side. The tangent of 13 degrees minus the tangent of 7 degrees. Now let's plug this whole thing into our calculator. Okay, so let's see. We have, I'm going to put this in parentheses, 120 times the tangent of 7 degrees, and then divide by, in parentheses, the tangent of 13 minus the tangent of 7. End parentheses, enter, and here we see that I get 136. So that means the value of y is equal to 136 meters. Now, some students make the mistake of stopping here, thinking, oh, I have the value of a variable, that must be the height of the mountain. But if you look at the diagram, you'll see, no, that's actually this length right here. Y is equal to 136 meters. Well, this is useful though, because now I know that this whole distance is going to be 120 plus 136. And so this 120 plus y, well, that's just going to be 256. So instead of 120 plus y, I can use 256. So I'll go back to this ratio here, but instead of 120 plus y, I'll use 256. Okay, so the tangent of 7 degrees is equal to the opposite, x, divided by the adjacent, 256. Now multiply both sides by 256. these cancel out, and now I can just find my value of x by plugging this in the calculator. So 256 times the tangent of 7 degrees, and if I round that, let's round it to the nearest tenth of a meter. So we're going to get 31.4 meters. Okay, so that means that this hill, if my calculations or if my measurements were accurate, and if my calculations are accurate too for that matter, hopefully they are, the height of this hill, the top of this hill above the level of the field where the measurements were taken, would be 31.4 meters, somewhere around there. So that, as you can see, is a bit more complicated than some of the other things we've done, but hopefully this also shows you that you can use these techniques of trigonometry to solve some more advanced and challenging problems as well. Okay, but let's take a minute to think about this situation a bit more, because in my experience, mountains generally don't have nice flat plains right at their base. Usually below a mountain is sort of a gradual decline, right, towards flatter plains, which often are far, far, far away. And from there, it might be pretty difficult to make these calculations unless you had really precise and accurate measurements. So if instead of having a nice flat plane field below, what if this was like a bit more sloped, right? Now that would throw my calculations off. And so let's think about some of the assumptions that we've made and been making. We've assumed that the ground is flat, but the ground isn't necessarily always flat. So it not being flat, that'll throw my calculations off. If it's slanted down like this instead of flat, horizontal, that'll throw my calculations off. Moreover, the Earth itself is not flat, right? The Earth is round, it's spherical. And so if I was measuring a large enough mountain from far enough away, would the curvature of the Earth cause my calculations to be incorrect or significantly incorrect? Now, these calculations already probably look fairly daunting, and this is just unit 1. So, maybe we're getting a little bit ahead of ourselves here. I do want you to see that these trigonometry tools do have a lot of power. There's a lot of, they're like a toolbox, and they enable you to do some pretty powerful things. But, maybe we need to back up a little bit, because problems of this level of complexity, especially if we're going to take into account slopes below the mountain and things like that, maybe we need to hold off on this and revisit it again towards the end of the course. So we're probably going to do that, and we're going to wrap up our study of trigonometry here. Now, this is not obviously a complete study of trigonometry. Think of it more as an introduction to right triangle trigonometry. And now let's talk a little bit more about measurement, the idea of area, and also a little bit about some of the assumptions that we've been making, and think about whether those are good assumptions to make. So in the next video, we'll start taking a look at area and then assumptions. Hope to see you then.